Hi, everyone. Welcome to Foresight's Molecular Machines Group. I'm so delighted to have Brenda Rubenstein with us today. She'll be discussing computing with molecules, storage and computation using small molecules and their reaction networks. We've had the absolute pleasure of having you on already for a workshop and welcoming you to our community. And now we're really excited to just hear a little bit in more detail what you're working on. I'll be in the chat monitoring for questions. And yeah, please take it away. Thank you so much for joining. I really appreciate it.
Sure. Thank you, Allison, for the introduction. And thank you to the group. I really love this group. I've been trying to participate for the past few years because this is a group that thinks big as opposed to small. And sometimes in some of the communities I live in, we think a lot for 40 years about one equation, and sometimes that equation doesn't matter. And so I like interacting with people who think bigger. And so today, what I'll be talking about is really collaborative work. I was one of the team leads here that has focused on computing with molecules. And here specifically, we're interested in computing with small molecules that can also chain to larger molecules like DNA and potentially molecular machines like you've thought about them before. But we are focused on small molecules. And that's because we're very much interested in their ability to actually store different kinds of information and also to use their reactivity. So small molecules can react in different ways than, let's say, other things can. DNA is an amazing molecule, has lots of great properties, but it's not the only molecule. And it's also not the only way that things can react and perform different kinds of functions. And so we've been trying to understand that over the past few years. So for those of you who don't know me before I dive in, I just wanted to mention a few things that we work on in my group. I guess I'm traditionally a theoretical or computational chemist. In some of the meetings, you may have heard me talking about different kinds of prediction methods. So one thing that we work on in my group is developing different kinds of computational biophysics methods. And most recently, for example, we've been finding ways to, I'll call it hack AlphaFolds in order to predict both dynamics and conformational ensembles of different proteins. And the reason why we're interested in this is even though AlphaFold was designed to predict, let's say, the ground state structure of a protein, proteins access many different structures. And if you want to think about function or machines, you're really thinking about how do you move between different conformations. And so we worked on different ways of being able to really rapidly predict conformational distributions. Not fully accurate, right? It's not perfect, but it gives you a lot of information about what mutations can do, what different kinds of evolution have done to proteins in a way that people can try to understand what's going on in things like cancer proteins and other proteins of interest. We've also done a lot of work in quantum mechanics, so most people know me for that work. One recent thing that I'll just highlight is we've been developing new ways to do molecular dynamics, so understanding how molecules move around on quantum computers. And so the way that we've done that is even though quantum computers can't give us an exact answer or a large answer right now, what they can do is they can provide some highly accurate energies. We can use that to actually improve other answers. So the basic idea is we can train neural networks on baseline knowledge that we have of a molecular system, then we can use quantum computing selectively to improve those networks to predict dynamics and energies and so forth of our systems. So we're trying to apply these to different biophysical systems right now. And today what we'll be talking about is really the third area where we focus on alternative computing. So how would we compute using different things that aren't traditional things? And we'll be focusing on different small molecules for today. So I'll start by discussing some of our molecular storage techniques, then I'll go into some of our computing strategies and maybe leave off with what I think are some of the bigger questions in this type of computing, which are honestly applications questions. I really think applications are what have been holding us back, not our technical capabilities of finding reactions, but really, what are we actually trying to achieve here? So the motivation for this, maybe I don't have to convince this audience, is that we're very much interested in trying to shrink down computing and also to make it much more energy efficient. And so I always start out with this example just to give us a sense of what computing has been and the sizes and scaling of computing. So this is the first, I'll call it computer that I knew. So when I was 3 or 4 years old, this was a printer in my basement. Actually, my basement until about 5 years ago, my parents' basement until about 5 years ago was filled with things like this. And of course, at the time, people said this was super compact, right? So highly efficient. But, it was so compact that I could actually hide in here as my 3-year-old self. It was a great hiding place. It was awesome. Can't really do that today anymore. But that says a lot about where computing has gone. So we used to have these massive tapes and, massive, even printers, not even mainframes, but we've gotten much, much smaller. And, just one example of this is one trace of Moore's law. So I like to look at this figure because what it basically does is it shows the growth in our computational power in units of calculations per second per $1,000. If you go back, you can see that we're roughly in the 1950s, 1960s, around 1 calculation per second per $1,000. Today, we're up to at least 10 to the 15, likely much more in many situations. And that's an amazing growth in computational power. And the sizes of the kinds of machines that we're making are also much, much smaller than years ago. And so it's amazing to think about, relative to the printer, but also for me, my grandfather was actually one of the people that first worked on UNIVAC. And, in his day, these ideas were crazy and, these things were huge. But now we can really talk about incredibly high performance computing that has truly changed our lives, even back from 1950, 19. It's amazing to think about. But many of you may know that even though computing has grown in these kinds of ways, that we are facing an end of Moore's law to some degree. Moore's law has stated that transistors on a chip roughly double every 18 months or so. It was really a prediction, but it's roughly held true. But we are facing challenges to Moore's law. Number one, transistors are getting smaller and smaller, which requires more and more money. And then thinking about physically, how are we going to make those super small transistors work? It's getting more expensive as a result of that. And obviously, we have lots of power demands and there's lots of heat dissipation that's going on. And so this makes us think about, can we compute in other ways that are maybe more energy efficient, maybe can also reach smaller scale sizes? So if you think of a size of a transistor, that's actually larger than many atomistic systems. You can't really have a transistor programming something that's incredibly smaller than itself. And so that leads to some issues. The other issue that's at the forefront today is also how much data we're generating. In some sense, this figure is even dated from 2020, where it's basically saying the world is producing 44 zettabytes of data every year, which is an incredibly large amount of data that in some sense we can never store. So the pace at which we're generating data, so if you look at, for example, the blue curves here, is much larger than the pace at which we're creating ways of storing that data. And it's unlikely we'll be able to catch up. And yes, there are ways around that about what you save and what you don't save. But if you did even want to save the important things are still growing at a much more rapid pace than the devices we're creating to store things. And so that creates a large problem about how we're going to continue to store things, how we're going to create things that are energy efficient, but also small enough to do all that storage. And so that brings us to the thought of maybe thinking about how can we store things in molecules. Small molecules are smaller than the sizes of the transistors that we're thinking about. So if you think about the nanometer scale, that's where essentially most molecules live. So if you think of even N2, I'm not saying N2 is useful for information carriage, but N2 is about the scale of 1 angstrom. And so that's much smaller than the scales of the transistors we're talking about. And so why don't we start to think about what you can do with molecules? Molecules are also very abundant. They're basically found everywhere. Molecules, in principle, have lower power demands. I'm not sure that everybody has put strict bounds on this, but at least the thoughts that are out there suggest that they have lower power demands to perform different operations. We never really have to worry about necessarily running out of molecules. And molecules can act in an embarrassingly parallel fashion. So they can react, in principle, in parallel. And you can manipulate them with many of the skills and reactions we know from chemistry. And so just one thought experiment that I did many years ago was that if you're able to store information in every water molecule in a flask, then we'd be able to store basically 200 Empire State Buildings worth of 1 terabyte, standard 1 terabyte hard drives. So that's an incredible capability that the molecules could have if we were, in fact, able to use them to store information on those kinds of scales. One last thing that I should just emphasize about molecules as well is that molecules can interface with lots of different things. I was hinting at this before with relative sizes of transistors, but molecules can interface with things like soft robots and responsive materials. Molecules are inherently atomistic, so there's no issue with creating an interface and another interface. Molecules can directly react with these kinds of systems and perform different functionalities and change them. And so there's a lot of opportunity to actually couple different kinds of molecular robots, molecular computation to these kinds of systems. And molecules can do a lot of things in biology, right? Biology is inherently molecular and also small molecular. Lots of things in our bodies are controlled by metabolites. And so there is room for small molecules within biology as well. And so a key area for thinking about molecular computing is in contexts where potentially silicon can't go, or is challenged to go. And in many of these situations, it just makes sense to do things more directly, molecularly, than to go through a bunch of different layers and interfaces and so forth. Now, many of you have thought about DNA. We love DNA. DNA is an incredibly specific molecule. Its reactivity is very special in many ways, coming from a chemist here. But we know DNA can store information, it can compute. We're just going to look at things from a different perspective that is perhaps a little bit complementary here. Okay, I'm going to first talk about how we do molecular storage and how we've been thinking about doing molecular computing. There are a number of different themes throughout this. Maybe for the sake of time, I'll emphasize them as we go. So our first ideas in molecular storage, or how can we actually compute using small molecules in a solution? And I just want to make clear, draw the picture. Everybody says, oh, okay, you can store information in DNA. Absolutely, you can. But DNA is a little bit different. It is an ordered polymer. You have different kinds of nucleotides, and there's an inherent ordering there. Whereas if you think about molecules just in solution, these are disordered. So you can't just use some sort of sequential placement of molecules to store information. But what you can do is you can basically say, if you have some sort of bit stream, you can assign a molecule, or if you want to get more complicated about your encoding, maybe sets of molecules to different sets of bits. So let's just say in the simplest picture, you can assign a molecule to the first bit. And if that molecule is present in solution, you can say it's a 1. It's absent in solution, you can say it's a 0. And you can go down your bit stream and assign all these molecules to your different bits. And so what that entails is if you want to store information, you can basically put the molecules that you want that represent these different bits according to the 0s or 1s in a solution. Now, in order to be able to make this useful as a storage medium, you can't just write your molecules. You also have to read them out. And that's one of the complicated things that's also a little bit different than DNA. So if you're talking about arbitrary molecules, we can't just amplify arbitrary molecules, right? There's no PCR for a random molecule at this point in time. And so that means that you put a lot of pressure on the way that you're chemically analyzing your mixtures. Fortunately, we do have a lot of tools for doing this. So if you make a mixture of molecules to store data, we can pull that data out using things like mass spectrometry. So we chose mass spectrometry because it's general. It's just looking at the masses of different molecules. And so you don't have to necessarily worry about exactly which molecules you're talking about. I'll say that with an asterisk. There are reasons why you might be worried about molecules overlapping in mass space and so forth. But in general, it's not prejudiced towards specific kinds of molecules. And so we can store our messages in molecular solutions, and then we can read them out using different kinds of spectroscopies. And of course, the challenge here is that if you think about data, you have to do all this pretty exactly. You can't get mess up in what you're reading out or reading in, and just a few bits really does change things. And so you have to do this quite carefully. And that's one thing that historically chemists haven't spent a lot of time thinking about. Now, the way that we originally did this is we did this using what are called UGI molecules. So these are molecules that are multi-component molecules. For those of you who are not familiar with these kinds of chemistries, you can almost think about it like a peptide in terms of its backbone. But what it allows you to do is put different R groups in different places. And the reason why I was personally interested in this originally was because if you can put different R groups on these molecules, you can get a lot of different possible molecules that are unique that you can use to store different bits from not that many different R groups or functional groups. So, for example, if you had 10 functional groups in position 1 and 10 in 2 and 10 in 3 and 10 in 4, right, then you have 10,000 different possible molecules you can make. And so that synthesis is not bad at all. It's combinatorial, but also what's important about these reactions is that they're very high yielding. And these molecules sit in a deep free energy minimum. So when they're made, they are made, and there's really very little to disrupt them. And there are no natural enzymes that are going to degrade these things, unlike other molecules. And so me as a theorist, I doubted that they would have the yield that they did, but these molecules have an incredibly high yield. And so we can actually synthesize them extremely high throughput. And so this is what I thought, why don't we be clever from the beginning and try to use resources efficiently? It turns out what we've done since is you can use any molecules anything will work in this kind of setup. As long as you can distinguish the molecules, you can use them as information carriers. So we did our biggest demonstrations using these OOGIs, but you can use metabolites. We've done that. Phenols. We can use different catalysts. We've used, if I have time, I'll show you, we've used actually chemical waste products. So we probably shouldn't say that, but we went around to different labs at the university and we gathered chemical wastes and actually used those for storage. All of these things work as long as you know the signatures of the species so that you can identify them in your solution. So how would you write something? So what you can do is just translate it into a bit stream. And again, just assign different molecules, as long as they're unique, to these different bits through presence or absence. And then again, if you want to get clever, then you can do some more complicated mappings to these different bits. One thing I should say is that, originally we imagined, why don't we just dump everything in the same solution? Of course, that doesn't quite make sense because we are limited by the kinds of spectroscopies that we have. And so it actually makes a little bit more sense to space these out physically. And so in most of our demonstrations, we've used weld plates, just typical biochemical weld plates. And so we've separated our mixtures into different weld plates, and then we just know which weld plates correspond to which places in our messages. And this allows us to more readily focus on what's in those specific solutions. And it also prevents us from using, a billion molecules. Instead, we can use, let's say, 1,000 molecules instead of a billion, because we can use 1,000 in one mixture, 1,000 in a different mixture, and so on and so forth. So that's the kind of setup that we have. And we can do this all high throughput because the synthesis is quite simple. Like I said, we have very high yields. We haven't found otherwise. And so this is actually important because if you're thinking about molecular storage or computing, you have to get things right. Chemists aren't so used to getting things right. And so when we first went into the lab, one of my first graduate students who was wanted to be a theorist, but he was helping us out. They would go into the lab and pipette things. And the problem is when you're pipetting so much data, this just becomes incomprehensible. Errors are introduced just through, humans trying to pipette or not understanding what's going on and so forth. And so we very rapidly moved on to different kinds of combinatorial syntheses where we can actually plate things very quickly. So these are different well plate examples, and we can get our mixtures by combining these different kinds of well plate patterns within our machines. So some of our first AIs for doing this were very small AIs, like this one over here. But then we moved to things like acoustic liquid handling, which will literally just move nanoliter droplets from place to place very rapidly so that you can make different kinds of mixtures. I'll get back to this, but this is one of the issues. If you do want to make a mixture, there's time involved with making these mixtures. Even if all your molecules are prepared, everything's set up, or you ordered them off the shelf, you just have them off the shelf, you still have to mix these things. And so that is one barrier for storing information in this way. We use spectrometry. Like I said, we use mass spectrometry, specifically FTICR mass spectrometry, because it's incredibly accurate and it goes, it scales across large ranges of masses, which was important for not being specific to specific kinds of molecules. So anyway, we would put these things together. Maybe I'll spare you the workflow for now. We have a nice little video, but I'll skip it just for the sake of time. Let me just show you how this goes in terms of what we see in the mass spectrometry. And this is also a message that I want to deliver. AI was incredibly powerful for us also being able to interpret what's in our data. So if you look at a mass spec, any sort of mass spectrum that you're getting from a molecular system, it turns out that it doesn't just show the one mass that you might expect. Me as a silly theorist, aren't you mostly just getting one mass? If anybody remembers organic chemistry, you get lots and lots of different things from fragmentation patterns that happen in these molecules. But you also get lots and lots of different peaks in your spectrum that correspond to isotopes, that correspond to ions that are just in your environment. So there's a lot of noise in these spectra. You get lots of different peaks. So if you just want to go around and hunt for the mass that you expect, it might be there. It will be there, but it might be buried in all these other kinds of peaks. And that's one thing that at least I didn't initially expect. In fact, from one mixture situation, so if you have one mixture that you're storing data into another mixture that you're storing data in, you might get completely different peak heights. And it just has to do with what the environment is that day in some sense. And so you can't really go searching for peaks. It's not very efficient. And so what we realized, looking at spectra like this, so this is if we're storing, let's say 32 bits here, you see a ton of different peaks all over the place. What we realized that we need to do in order to make this happen is that we have to do some type of multi-peak statistical analysis. analysis. We ended up using random forest to try to pick these peaks out. And it was incredibly important for us to be able to actually find our data when we have thousands of different species. So what we would do is we take our plates and we'd actually learn what are the key features of each molecule that we're trying to find. So we'd always reserve part of our data plate, train on that, and then use those key features to figure out what's in everything else. For example, we did an example where we're storing things in metabolites, and this is the guanosine. And guanosine has a bunch of different peaks on the left. And the peak counts can vary from day to day. This is just showing that the largest peak was the guanosine associated with sodium. But what we can do is we can, let's say, search for the 10 most indicative peaks that should tell us, do we have guanosine, in fact? And if we do that, we basically get a detection accuracy that's close to 100%. If you don't do that, your detection accuracy becomes very low. And so this was an important thing for us to do, and it makes our system entirely high throughput, right? So we can form our mixtures high throughput, we put them through the mass spec high throughput, and then we can also do the analysis high throughput. Very important for storage. So let me just say the kinds of things that we've looked at. So we've stored different images of different forms. I'll say I didn't pick all these images, lots of Egyptian images, but there's a Rhode Island flag image here, just for the sake of fun. We've gone up to large images, including Picasso, and where we were at, in terms of pushing our storage is somewhat impressive. So the red dots on this plot in terms of total data stored were state published. So that's genomic data. And of course, this is a log scale, I'm not hiding it. Genomic data is definitely storing more. But for those of us working in the non-genomic world, we're actually able to get to pretty high data storage. So at this point, we're close to a gig. I don't have that point here. We're close to a gig without doing genomic data storage. And we've done that in a few years because this combinatorial approach, which can also generalize to DNA, is a relatively powerful and simple one. And, in fact, in many DNA demonstrations, you do have combinatorics because you have different strands and so forth. So we were actually able to store reasonable amounts. I think in this table, this is from 2019 where we were storing Picasso, but we've been able to go up to a gig since then. Now, what's holding us back in terms of storage? It's really the ability to write information. So like I said, if you want to assemble these mixtures, you have to move your plates around and you have to actually move chemicals from one place to another place. And so that's our threshold. It ends up not being the reading. We can put things through the mass spectrum really fast, or maybe you want to use some other technique. You can do that pretty high throughput. It's really in the writing, physically moving things together that limits us. And so you can see this in the blue curve that I have on the right. We're limited there, that the read is relatively fast. And so that's a challenge. How do you actually move things faster? We have some thoughts on that, but it's not the easiest thing if you just use the parts off the shelf. Lastly, I'll just emphasize for the storage, again, we can use anything. In our most recent paper, we were just showing that we can store the recycle symbol. And the way that we can do that is we can use a whole bunch of different chemical wastes. For example, we would take, so I'm showing different library elements on the right here. These different elements have different signatures. And these, we actually don't even know what are in these wastes. These are 7 different example wastes, but we know what their peaks are. And as long as we know what their mass spectral signatures are, we can then mix them together and then we can get that data out. That just shows that we can essentially use any reasonable set of molecules and we can potentially do things in a somewhat sustainable fashion. You reuse molecules that are just out there as opposed to synthesizing everything from scratch like I thought to do at the beginning. So that's where we are in terms of storage. Like I said, what we're doing is we're trying to understand what happens if you have chemical diversity, really monomer diversity along this x-axis, whereas in the past, people have mostly focused on polymer diversity. And these are, in some sense, complementary axes. You can imagine you can increase your capacity for data by mixing the two. And that's really the approach that I would suggest moving forward. So that's data. We've spun this out as a venture that's looking at really discrete data storage. And one reason I also want to make clear about why we spun some of this out is just because this lied at the interface of chemistry and computer science. And there was a lot of, certainly at NSF, of, well, it's not chemistry, it's not computer science, we like it, who takes it? And so we got tired of those kinds of arguments. And so we spun it out, and Atomics is up and running and hiring. And so we're very happy to continue the storage adventure. Now for computation, in the time that I have left. Computation is always the harder thing. It's the thing for me as a theorist that I think about quite a bit because it's an interesting topic. How do you make things compute that otherwise wouldn't? What we came up with in terms of computation is we wanted to use these small molecules because of their reactivity to potentially form different kinds of neural networks. And so in our first examples, we thought about how can we make molecules act like perceptrons. And I'm sure, as all of you know, perceptrons are binary classifiers that are able to classify, let's say, between a cat and a dog given different inputs. And so the way at least my thinking went at the time is that chemistry can actually do multiply accumulates very well. So if you remember in things like perceptrons or really any neural network, you take a weight and you multiply it by an input. And then you sum over all those weights times inputs. Chemistry can do this well. You can imagine your inputs being the chemicals. The weights could be volumes, they could be concentrations, they could be kinetics. There are a lot of different things in chemistry that naturally serve as weights. And so we can automatically get away with this multiply accumulate without doing anything. All you have to do is basically combine your volumes together in different ways and understand what you have once you've combined all those things. What you also need for things like perceptrons is you need some sort of nonlinear function to threshold, right? So you need to make a decision between cat and dog. So you need to have some kind of threshold. And so for a while, we really spent a lot of time thinking about how do you do that chemically? And then we realized after probably longer than I should say that any autocatalytic reaction actually just does this for us. And so if you deal with different chemicals or molecules that are autocatalytic, we can just let them do this threshold on their own. So in our first demonstrations, what we did is we didn't implement the threshold, but I'll talk about that at the end. We literally did use our weighting in terms of volumes. So we take different concentrations of chemicals, and then we weight them according to their volumes. And we did this kind of the automated mechanical way at first, but then we went fully chemically subsequently. So here's an example of what I'm talking about. So what we wanted to originally do is classify different images. So we made super small MNIST images, and we plated those images in terms of different chemicals. And what's nice about these different chemicals is honestly, we can just put them all together and then we can try to recognize them all at once. And so that's using the parallelism of molecules in chemistry. They can all exist in this space at once as long as they're not reacting with each other. And we can recognize all of these images all at the same time. So what we would do is we would train. So at first we train a neural network offline. And I can talk about online training in chemistry, but we did offline at first to recognize these images. And these different weights we would implement as volumes that we would take out of each and every well. And those would be our weights. And then we would pool all of those different volumes with the different molecules. And then originally we would threshold them in some sense ourselves. So we would measure, okay, how much do we have of each different molecular concentration? And then we would determine, do we have a match or don't we have a match? And so this was an automated way of doing things. We had pretty high accuracies, 96, 97% accuracies, classifying different kinds of images and vectors. But again, it was still mechanical. We're not getting at real chemistry by doing this. We are storing things in molecules, but we're not operating chemically. So we wanted to push that further. And like I said, what we realized is that actually autocatalytic reactions can do different kinds of nonlinear thresholding. So originally when we thought about this, we kept saying, oh, isn't pH a nonlinear threshold? Not really, because it's on a log scale. And then it took us some time to realize autocatalytic reactions actually do this. So for those of you who are not familiar with autocatalytic reactions, they're a huge number, but they're incredibly important just in the evolution of how molecular, I'll call biomolecular computation in our bodies works. But the basic idea for these reactions is that they involve a molecule they basically, as a reactant, use a product. So what would happen in these kinds of reactions is you start with some amount of, let's say, reactants, and then these reactants react to produce a product. And then that product actually helps catalyze in the formation of itself. And so this happened to be a very specific reaction that came out at exactly the same time we were interested in these reactions, came out of the Whiteside's group that's also interested in molecular computing. It's really, you've heard of click reactions. It's basically a click chemistry reaction. And the idea is that when we combine different kinds of azides and alkynes together, they're going to form this tris product. And this tris product actually catalyzes the formation of itself. And so the point is, over time, you're going to see this nonlinear threshold. And so we can use this by using this reaction as our input. So here's one example, just so that you get a sense of it. This was one of our early networks, a winner-take-all network. And the idea here is that the network that recognizes the image that the network is looking for is going to threshold first. So what we can do is we can take data. Maybe we can take some of these Caltech silhouettes. Here's the Rhode Island anchor again. We can plate this Rhode Island anchor in terms of the catalyst. So in terms of the product, so we put a little product where the blue is, and there's no product where the gray is. And then we can, again, encode different neural networks to recognize these images as weights that are volumes that we're going to extract. And then we'll pool those volumes together from the different places on our plate. And then we're just going to let the reactions threshold themselves. So the autocatalytic reaction should threshold itself if it matches the image. So if the network matches the image, that should be the first one to threshold. And so if we plate something like the anchor and we aim to recognize the anchor, that's what our neural network is supposed to recognize, then anchor should come up first here as number 3 and win this winner take all. And so we're able to show that this works. And so you'll actually see that the first thing thresholds first. So great. We can do this, still not quite what I'd call computing. It's essentially one layer. Nothing completely interesting is happening yet. It's just showing that we can do this. And the other issue with this demonstration is we only use positive concentration. So if you think about chemistry, you usually have positive concentrations. I haven't heard of many negative concentrations. And so that's an issue. If you think about neural networks, you really need multiple layers. You need negative concentration. So how do you do that? And that's one thing we've been working on recently. So let me just say a few things about that. So what we've recently moved to is what we call a dual rail encoding. We're not the first people who've ever thought about this, but this works for chemistry. Our first demonstration used acids and bases, which is fine. I'll show you. We've graduated from acids and bases. We originally wanted to say, okay, this is simple, but acids and bases cancel each other. So there are issues with that. But nonetheless, what you can do is, let's say you wanted to encode a 1, you take 2 flasks. So one flask is, let's say, an acid, and your complementary flask is a base. And if you want to encode a -1, what you would just do is flip those flasks. So you would just keep an eye out on what rail you're working with at different times. And if you flip, now you get your negation. So now you have completely positive concentrations. You're not making your concentration negative. You're just, flipping what rails you deal with. So that actually allows for real circuits. If you want to go the circuit route, you can do ands and so forth, but then you can negate those ands to start making real circuitry. And so we had some demonstrations of this. Let me just say, acids and bases do cancel. And so we wanted to say, can we do something using autocatalytic reactions that shouldn't cancel and they should threshold? So we'll have a paper out on this very shortly. But the basic idea here is, again, we can use dual rail, but now we can do it in terms of autocatalytic reactions so that they'll threshold on by themselves. And the other thing is that they're not going to cancel each other if you pull. We create rails, let's say A and B and A prime, A bar and B bar. And we do our logic on those rails in some sense separately. Sometimes we have to bring them together, but we can do that logic on these rails separately and then obtain the result. So this is just showing, for example, how we would do an OR. OR is trivial because you're just mixing 2 sets of chemicals together and saying, is it above some sort of threshold? And, if you had a 1 and a 1, you'd be above the threshold. You'd have enough catalyst to be above the threshold. If you had a 0 and 0, you'd be below. OR is trivial. And is a little bit harder, and we have to put a little bit of a bias in, but then we can also say, do things threshold above a concentration? But then we can start making real circuits. We've done full circuitry at this point. So we have a half adder, recoder, these kinds of things, fully chemically, but all dual rail, and we can do multiple layers. So right now it looks like we could do 4 or 5 layers without having to replenish anything or check anything, which is much better than what we've seen before. Certainly acid-base chemistry doesn't do that. But I would say that cascading is a key problem in any sort of these molecular schemes because things do dilute. And so one thing about autocatalytic chemistries is that they do replenish themselves in some sense. So those are the basic ideas. And right now we're working on more complicated networks, so that paper will hopefully come out soon. But just one thing that I would say, having thought about these things, I think we can come up with interesting tricks for doing computation. We can come up with reactions that can do different things. Given dedication, chemistry, funding sources. The government believes in us, not just us, but the community. I think what's really holding things is real applications. When you talk to chemists, they don't necessarily get excited about this because they say, what chemistry does it do for us? Is it going to be the automated laboratory for us? Is it going to do environmental remediation? Is it going to do biological healing? And they're just not seeing that yet. So a lot of people aren't biting. And so I think that's really what our community needs to think about. And we're also trying to think about, how do you tie this computation to real applications? You use the computation as an intelligent sensor, hook it up to some real chemical actuation, and then you have interesting things. And so that's just one thing that I want to clearly convey. It's a strong opinion of mine. I love this area, but unfortunately it hasn't caught on as much as it probably should, because people are looking for that, what's that $1 million solution, both at funding agencies and elsewhere, before they can really believe in it. Suffice it to say, thank you for listening. What I've described today is a new way of storing information in disordered mixtures of molecules. We focused on small molecules and tried to show what they can do. Key thing with small molecules is that they have different reactivities than, let's say, a DNA, which is commonly used, which allows them to potentially operate on different materials and in different environments. And the challenges that we face, so for storage, we talked about the writing limitations that we have, and so we need to push the bounds there. For computing, I still think that there's a lot to go in terms of how we can efficiently use these systems. What are the best molecular systems for computing in what different circumstances? And in particular, like I was saying, how do we tie these different kinds of computations to real functions that people are going to care about? So with that, I'll acknowledge my larger team. Like I said, this was a full team effort. I'm a theorist. I think about things and come up with ideas, but really we had some great engineers. Jacob Rosenstein was an amazing engineer who was happy to work on these things. We also had an amazing chemist, and so Kim, who she doesn't know much about computing, but if I told her this is the reaction we needed, she knew how to do it. And so that was an amazing collaboration to make this happen. And I'll thank the funding sources for this. So we really got kicked off on this by DARPA. DARPA had a molecular informatics program for a while that has since ended. And then we were subsequently picked up by NSF. The challenge is that NSF is not sure where this belongs. And so it's been a challenge to find, larger, the kind of multidisciplinary funding that you actually need to do this kind of work. So with that, thank you all for your attention. I'm happy to take any questions.
Thank you so much. That was absolutely fantastic. Questions, comments? We have raised hands. So many of them. Are you okay with taking them directly, or?
Sure. Yeah.
Yeah. Okay.
Right.
Cool. Then Ted, please take it away.
Maybe Ted's first. Go ahead.
Hi. Ted or Ted?
So hard to know. Go ahead, Ted.
I know, really. Okay. So in a previous session of this group, we had Boris Feynman, and he said some pretty strong things about AlphaFold not working and things like that, and about protein chemistry. And I know this is not exactly your field, but I wondered what you thought about that talk, if you saw it.
Sure. So we do work in this field, actually. I didn't talk about it in this talk. It's actually exactly my field. This is what I would say. So Boris is 100% right. If you want highly accurate predictions, you still have to go the physics route, or at least at the very minimum, you got to put physics in your neural network predictions. You really have to be physics inspired. So that's absolutely right. And binding is a very difficult problem. But maybe I'm not quite as bearish on some of these AI technologies. My perspective for some of the AI technologies, which we have worked on, is that, the acceleration is incredible and there is signal in what it's telling you. So it's not perfect. It's not 100% accurate. It's not going to hit every single case. But for example, we worked on kinase prediction. So kinases are proteins that phosphorylate others and are involved in cancer. Because there's so much data on kinases, we could predict lots of different effects of mutations, lots of different potential dynamics. The data was there, and we can make these predictions. And I was actually surprised. And just to make sure you understand the difference here, the physics-based predictions, we did those. Took us 2.5 years. We started on those. ML took us 3 hours. Now, you know that the ML was right if you didn't have the physics? This is a question, but these are orders of magnitude, and the fact that it's mostly right is real signal that you can take into the clinic. I talk to people at the med school, and they say, if you could just tell us if this mutant is probably doing blah versus blah, like that's gold for them. They don't need to know necessarily exact. So it's a question of how exact you need to be. Some cases you do. Some cases, it's just, we need some information. We need it quickly.
Thank you.
Okay, next one we have Rocco.
Hello, is it right? So I wanted to ask more like technically, if I understood correctly, how you actually store this information, because you have there that you can store like 1 gigabit, but you cannot. This doesn't mean that you have 1 billion of different molecules and every one encodes the bit. So this means that you store it in different, like these little pockets or little droplets, or
Yes. Yeah, that's exactly right. If you had to do a very dense encoding and you did it all in the same space, you, let's say, need 1 billion molecules. So instead, we do use a little bit of physical space, which people do in DNA too. So we use wells, and then in those wells, we have smaller numbers of molecules. And then you can play tricks. Let's say if your data is not that dense, right now you can play compression tricks so that you don't have to use a molecule for every bit. But that's exactly right. One of the disadvantages of this kind of method is you will need a number of chemical species to represent your data.
And with that, so the application, because you mentioned it probably at the beginning, so to which you are directing is not really replacing like traditional computing.
Yep.
And there should be some niche application which maybe can deal with that. Because what is my general concern is that like traditional computers rely on the, let's say, positional encoding of information, which is difficult here. And because this positional encoding basically scales exponentially, like it scales much better. So I think with complex system, it always beats this chemical processing. If you
Yeah, I'm not sure about always, but what I would say is, yeah, we're targeting applications for which it would be hard to use, traditional computing. So we're targeting applications where you're already in chemistry, things are already wet. That's either biologically or in the lab or environmental conditions. And like you're saying, actually, in a lot of those cases, it's not large data, it's actually small data, but still hard to get that data in some situations.
Okay, thank you.
All right, Ted, now it's you.
Thank you. I really enjoyed this talk, Brenda. So one quick comment following up on the last question. You probably have heard many years ago there was a lot of interest in DNA computing for combinatorial search. And there was a lot of hype and discussion around that wonderful massive parallelism until people realized you'd need an ocean of DNA to solve interesting size problems, and it would take forever and so on. So I really like your point about instead of looking at trying to do after conventional computing, let's say these combinatorial problems, your point on doing sensors and actuators in chemistry seems really right on, because you're taking advantage of where you already are.
Right.
So that was my comment. I just had a couple of clarification questions. So if I understood correctly, for the storage you're putting together, that if you should think of it as an archival storage. I didn't see there was any easy way to edit once you put something in there. Is that right?
100%. So we've mostly been working on our archival. We have computation demonstrations, but again, they're smaller scale, and you can't use some of the same molecules we've been using archival. So the archival, we're looking for molecules that basically can't react and therefore don't degrade. But for computing, you need things that are much higher up in free energy such that they can't react. So there are different sets of molecules used there.
Yeah, so that you would want it closer, that you could do something that will switch it, but only when you want it.
Exactly. Yep.
And then my second question is on the computation side. You mentioned it was the challenge of cascading to multiple steps due to dilution, and that you could use potentially autocatalytic reactions to replenish the chemicals. So I was wondering how hard it is to design different autocatalytic reactions if you're trying to do, say, a large network of these things. Is that a hard thing to do or an easy thing to do to come up with different ones?
Yeah.
Where does that fall?
This is a great question and a key question there. So if you want to use the same autocatalytic reaction, you're fine. There aren't a ton of these that are readily useful in different situations. Part of it is people haven't explored all situations, but in synthetic chemistry, I would say there, maybe 20, 30 off the shelf, and a few were recently discovered. There aren't a ton of them. There are ways to coax things to get you there. And so that is in some sense a limiting factor. But I think we also see that honestly in biology. We do have a lot of autocatalytic reactions in biology, but it's not necessarily that many types of them. It's similar chemical systems.
Yeah, I think so. Maybe he's going back to your point about where this fits with NSF and so on. That so that if you think of the computation side, there are people who think, oh, I want to do lots of computation, many steps, high reliability. It's the normal what you think. In chemistry or biology, you said that's not necessarily, it's not necessary to do interesting things. And so that again is, I think your focus on applications of what would be useful to do in the solution in a relatively small number of steps is spot on. So thank you.
Yeah, I agree.
Okay, Ted, it's you again.
Okay, so a trivial question: how do you store a 96 well plate overnight, and how do you store it archivally?
Actually, for us, the molecules we've mostly been using for storage, they basically don't react. So to be honest with you, we literally just put styrofoam, cellulose on top of it. That's it, and it's out there. So we did experiments, and if you just store it like that, room temperature and everything, it doesn't degrade over the 5-6 years that we've been watching. We've been able. It's just because these molecules are so in their free energy minimum.
Mm-hmm.
Nothing's going to get them. I mean, not nothing, but
Right.
new things are going to move them out. In cosmic radiation, yes, if there was a ton, you could start fragmenting, but we haven't seen anything.
Right. Yeah, this is a wonderful talk, and all three of the areas you're working in are amazing. Really, thank you.
Thank you. Thank you all.
Fantastic. Is there any other question before I jump in? Okay, great. I would love to maybe double click on one of the points that you mentioned in the abstract, which is the point of intelligent molecular machines.
Mhm.
Would you mind possibly filling that in a little bit more? I'm not sure if you mentioned that much, but it sounded very intriguing.
Yeah. So we're touching on this, where's the place where this goes? So we can use these different kinds of chemical reactions really as sensors. These networks can sense different concentrations. So if you program your network to be able to recognize different kinds of concentrations of different inputs, now you can use that to sense, and then you can transfer that over to different kinds of machines. That's exactly what we're trying to focus on, is connecting the sensing to the actuation in solution. And so by intelligent, we shouldn't be able to just, so there are different demonstrations of, we saw the pH change, but that's just one input. What you're really talking about is many different inputs that you can feed into the network, and then you actuate based upon that. So that's the basic idea.
Okay, wonderful. Ted, is there another question from you with your hand up? No, okay, it's done. Wonderful. Is there any other challenge that you'd like to point out? I know that you pointed out the application space, and we discussed it a lot now, even during the discussion, but is there anything on the horizon that you perhaps didn't mention, perhaps that was too speculative or something that you want to bring up?
Yeah, so I think Tad got at this. The parallelism is always an issue. It always feels like it's there, but then it's not in chemistry. There's cross-reactivity. There's issues with dilution. It is a challenge. It's an opportunity, but also a tough challenge. And also, as was mentioned, it's making networks do interesting things that aren't too complicated, that aren't too chemically specific. Specific by this is the only network we could ever make that can do things. And there's a lot of breadth in chemistry, but we haven't looked at all those corners and trying to understand what's the most useful chemistry and to create the chemistries to do things. That's oftentimes a challenge. So there's almost a world of things you can do, but what world is the best world to live in? That's a challenge and develop around.
Yeah, it's almost like too many possible applications down the road, but not one near term. So it's always more efficient to do something like a small incremental progress in another field near term. Yeah, we definitely do know that. And is there any way in which people can, stay up to date on your research? Is there anything you want to point out in terms of future collaborations? Any pieces that you mentioned where people in this group, if they want to help you work along, if they want to support it, what should they know?
Sure. So we're always happy to collaborate with experimentalists. We're very much interested in this actuation piece of really thinking about what are excellent, tangible applications, and love to collaborate there. I guess in terms of other things that we're interested in, we're also always interested in predictive vehicles. And one thing that I guess I was mentioning the last time I was with the group, we are interested in the original molecular machines predictions, and we've been trying to do some modeling around that. I'd love to give a talk on this of, can you actually realize some of the machines that this group historically read about in chemistry? And The answer is in many cases not quite, but there are other ways of getting around it. So maybe that's another talk for another time. But I'd love to share that manuscript once we try to start writing around it with this group.
Wonderful. We have to go ahead then and schedule you for another talk if you're open to it. Thank you so much for taking the time. That was absolutely breathtaking. I learned a lot. Thank you so much for your fantastic questions, everyone. I really appreciate everyone taking the time. And yeah, that was really exciting. That space is barely open. Thanks a lot for your wonderful work in that. And I hope to see all of you for the next seminar. Thank you so much.
Thank you, everyone.